Okay, welcome to lecture 12C. I am just uploading lecture 12A and 12B. And now let's go over some of the lecture material which we studied in a previous lecture. Now, if you recall, this was from our previous lecture notes, and what I did was I started with this spring mass oscillation system, F equal ma, and then I did work out all this, and later I arrived this expression y prime. Y is in fact a dimensionless quantity, but again here note that y double prime here involves dimensional t. T here is not non-dimensional. Only y is non-dimensional. This is dimensional. Okay, so when I say this particular ordinary differential equation, if you solve this directly, then you're solving the non-dimensional y solution when the dimensional time is changing. Okay, so this would be the solution when the t is, this is a non-dimensional solution of y when t is dimensional. Okay, whereas the last chart I show you that here, if you solve this equation right here, this instead of y double prime, if you have a y double dot, then that is completely non-dimensional in both y and t. So I'll make another note here that from the previous notes, that this one and that one, both y and t are non-dimensional. Okay, so if you solve this ordinary differential equation, at the end you come up with this. Okay, that was your solution right there. Let me box this. Okay, with this initial condition. All right, so that's the solution right here. This is your final solution. Now, in the previous lecture, I didn't show you how I got this constant A and constant B for this one, A and B. Okay, but I'll show you that today. And if I give you more thorough summary here, I'll put a note here that you already know. Tau d star is 2 over b1, and omega 1 is already b1 square minus 4c1 over 2 square root, and b1 here is 5n over rek, and c1 here is 8 over Weber number k. Okay, so that's the coefficient that you'll have to use. So notion is that if you know the density ratio and which one is density ratio? This is density ratio and this is a viscosity ratio. And if you know the Reynolds number and Weber number, you know B1, C1. If you know B1 and C1, you know the non-dimensional relaxation time, and you know the oscillation of frequency oscillation, and then once you know all this, you can determine A and B, and you know all these coefficients, you can find the solution for homogeneous solution, and you know that's a particular solution. So general solution is homogeneous plus particular solution. All right, so in the previous lecture, I mentioned to you that we solve for y when both y and t were non-dimensional. But today's lecture, I'd like to solve the ordinary differential equation when t is non-dimensional, but when y is non-dimensional, but t is dimensional. And that's where we left off in the part of the solution here. This is what I'm going to go back to. This one right here. Okay, so let's see. All right. So that's y prime, c is constant, y ck at y2. Okay, so that's what I'm going to do today. So let's see. Now, so that's what I mean by you have a y non-dimensional, t dimensional. So if I write that equation, y double prime plus cd mu l rho l rho square y prime plus ck sigma rho l rho cube y equal 2cf rho g rho l u square rho square. Okay, that's the equation that we are solving. And now first, what do we want to do? We want to solve a homogeneous solution, right? So here, if you solve this for y is y homogeneous plus y particular. Okay, so for y homogeneous solution, I have y double prime plus cd mu l rho l y o square y prime plus ck sigma rho l rho cube y equals 0. Okay. Now, I will say that this is equal to B, and let's say this is equal to C. Then my governing equation looks like y double prime plus B, y prime plus C, y equal to 0. Now, does it look pretty easy? Yes. What's my characteristic equation? Characteristic equation would look like lambda squared plus b lambda plus c is equal to 0. Okay, so what's my lambda? Lambda will be minus 2b plus minus b squared minus 4c over 2. Okay, so now if you say that b squared minus 4ac, excuse me, uh, 4c is less than 0, okay, then lambda is for plus minus I okay, I'll Okay, I'll just do a 1 over tau d. Okay, isn't that what we did in the previous lecture? Let's see. Alright, so that's what we did in the previous lecture. That is equal to tau d star. Okay, this is non-dimensional, right? Okay. Plus that, so where you have tau d is equal to 2 over b, okay, and omega is equal to b squared minus 4c over 2 of that. Okay, so this is something to remember, I guess. Okay. All right. Then you can easily get the solution of y, b, y homogeneous t will be exponential. Okay. 1 over tau d t. Okay, now this is dimensional t, okay? And a cosine omega t plus b sine omega t. Okay, here I will say that tau d is 2 over b. Okay, also if you square this term, that's b squared over 2 minus minus what? Let's see. Okay, that's 4, by the way, 4. Okay. And minus 4c over 4. Okay. So this will be 1 over tau d square, right? And this goes away. Okay, so that'll be 1 over tau d square minus c. What is minus c? C is right here, so that's ck sigma rho L rho 3. Okay, so that's the solution of homogeneous solution right there. All right. Now I want to go over the particular solution now for particular solution. Okay, particular solution, if I write y double prime plus cd mu L rho L rho square y prime plus ck sigma rho L rho 3 y 2 cf rho g rho L u square rho square. Okay, now I'll call this this thing B, I'll call this thing C, I'll call this entire thing as D. Okay, then I know y double prime plus b y prime plus c y is equal to d. Okay. Now assume that assume y particular solution is some constant. I don't know what that constant is. Okay, then I know y prime is 0, y double prime is also 0. Okay, now if I substitute this back in here, then I'll get what? I'll get what? Substitute right there, then I'll get 0 plus 0 plus c times a certain constant will be d. Right? So what is this constant? What this constant is d over c. Right? That is your particular solution. Okay? Now, let's go on. Let's go on next page. Okay. I go to the next page. Then y particular solution is d over c. D was, what was d? D was right here. D was right there. And what was c? C was right there. Okay, so if I do that, d was 2cf rho g over rho l and u square rho square, that's d, over c. Okay, c was that, right? So rho l rho cubed divided by c k and sigma, that's 1 over c. Okay, then I could do, what can I do? I can get rid of this, right? I can get rid of that. Okay, so what I will have is 2 right there, and cf over ck, that's this, and rho g and u square and rho, okay, and sigma. And what does it look like? This look like a Weber number. This is a Weber number. This is a Weber number. Okay, and what else? What was CF? Do you know? If you go back here, CF was 1/3. This was 1/3. CK was 8. This was 8. Okay. So what is it? 2 divided by 8 divided by 2, that's 4. Okay, so that's, this whole thing is 1 over 12. That's Weber number right there. Okay, so this is what particular solution. Particular solution is Weber number divided by 12. Okay. All right, so now whether you use this particular solution of this case where we are assuming y being non-dimensional and t being dimensional, but in the previous case we had both y and t to be non-dimensional, but y particular solution doesn't matter because this one doesn't have any time dependence. Okay, this is non-dimensional, this is non-dimensional. So this particular solution here we found when we are solving the ordinary differential equation where y being non-dimensional and t being dimensional can still be applied without any problem for this expression right here, where we are assuming both y and t are non-dimensional. No problem. Okay, so we are using this. All right, so that was the particular solution. So so what? Now y is equal to y homogeneous and y particular. So y particular solution is this. Okay, let me change this. I'll say that this is particular, this is homogeneous, this is particular. Homogeneous is exponential minus dimensional t over tau b times a times cosine omega t plus b sine omega t. Okay. That's the final solution. Now I will say that you must evaluate A and B. Evaluate A and B using initial conditions. That is, y0 is 0, y prime 0 is y prime 0. Okay, so let's do that. Now, can I take the derivative of this? Taking derivative. Okay, y prime t will be, that goes away, right? So this times this derivative times this derivative times that. Okay, so I'll do this. This derivative of this is minus 1 over tau b. Okay, and then minus t tau b. And then just multiply by this. That's a times cosine omega t plus b sine omega t, that. Okay, now I'm taking derivative of that plus. Okay, derivative of that is this constant, so this one thing comes out, so minus omega a. Okay, this cosine changed to sine omega t plus this thing comes out, omega b. Okay, and cosine omega t, closing that. So derivative of that times this one, so that's exponential minus t tau b. Okay. So that's what I have. And now if I put this solution right here, y when t is equal to 0, that's y0 because of this. Then I have, what do I have? I have Weber number 12 plus, what is this? 0, that's 1, right? Times, what is 0 here? That's 1. Okay, that's 0. So 1 times 8 times 1 plus b times 0 will be this. So here I can find out that a is equal to, okay, y o minus Weber number divided by 12. Okay. Right? Now what about this one? Okay, that's y prime o will be, okay, minus 1 over tau b. When t is equal to 0, that's 1, right? And that's a. Okay, and cosine 0 is 1 plus b times 0. Okay, plus, what is this? Minus omega a times 0, that's 0, plus omega b times 1 times 1, okay? That is equal to y prime y prime 0. Okay, so this goes away, that goes away. Okay, so b here is uh, 1 over omega, this one because of that, and y prime, okay, plus okay, I put it in the wrong location. Okay, that, what is this? That's this one right here. Okay, that is, okay, this y o prime, that one, plus this term, plus a over tau b divided by omega. Okay, that's what I did. Okay, so b here is 1 over omega y 0 prime plus 1 over tau b. What's a? A is y0 minus omega Weber number 12. Okay, that's b. Okay, so is this, let's check what we did last time. In the previous lecture we had I told you that we will come back to this later, right? I told you we will come back to this later, right? So this is how I find a particular solution, which you already know. This is how I find coefficient a and b. Coefficient a and b. B looks like this, okay? Here b looks like 1 over omega. Now this omega and that omega is different, okay? Because this omega is the non-dimensional one, this is the dimensional one. Okay, but they follow the same form. Okay, that this, like this, and like this. Okay, that's B. A looks like that, like this, minus, like that, like that. Okay. Now A should be same because A is free of t. Okay. T here are different, but A is free of t, A here is free of t, but B here is not a free of t because it involves this, it involves that. Okay? So they're different. B here is different. Okay? Now, so that's what we did previously, and that's what we are doing now. So if I summarize these solutions, I can finally say that we can say that yt is Weber number divided by 12 plus exponential minus t divided by tau b times a times cosine omega t plus b sine omega t, where you have a is equal to y minus Weber number divided by 12, and b is 1 over omega, and y 0 prime plus 1 over tau b, y 0 minus Weber number 12. Okay, and what else? I want you to know that tau okay, I keep putting this tau b as tau d or vice versa. Okay, it doesn't really matter, but let's call this d. Let's call this d. Okay, let's call this d. Sorry about that. Okay, because previously I called this all d. This is d. This is d. This is d. This is d. Okay, this is d. Alright, I'm sorry about this. Okay, if I do, then this d will be 2 over b, and omega is b square minus c. Okay, now what else? Maybe you should also know that b and c, okay, b was cd and mu l rho l rho square, and c here is ck sigma rho l rho 3. All right, do we have any d here? D really didn't matter because we start with d, and d was just used to express the particular solution, and particular solution came out to be just the Weber number expression. Okay. All right, I'll put a note here that Weber number here is rho g u square rho divided by sigma. Okay, so that's the final solution of this droplet breakup model. All right, so you can plot this and find out. Find out this. Let me go back. Here, what was my... Okay, if you go back to my previous lecture, lecture 12, I mentioned about this to you, right? So you find y, you solve for y. Do you know y? Yeah, you know y. Okay, you know y, you know how to find y, and plot this. And once you know y, then you just divide it by 2, and then add 1, and that will give the ratio of this edge over this initial radius. So you start with 1 and then it will go like this. Okay? So I want you to draw that using this expression right here. That's your homework. Okay? And if you draw this, that will be on x-axis you have a dimensional time, and y-axis you have a over RO. Now, but if you draw this where pretty same equation, but this equation is even not only y but also t is non-dimensionalized. So if you plot this one right here, if you plot that one right there, then your solution will be x-axis you have a non-dimensional time, y-axis you have this a over r. Okay, so I want you to plot both non-dimensional one and dimensional one, and make sure that they're same trend. Make sure they have the same trend, except that the magnitude of the x-axis values will be different. Okay, yeah, and that's all I have for lecture number 12C, and I'll see you in the next lecture. Bye-bye.